but today we have Magdalena Siwek, who has recently obtained her PhD from the CFA and will be starting a Simon's postdoc fellow in Columbia in the fall. She's going to tell us today about massive black hole binaries and circumbinary disks. Take it away.
Thank you. So first off, I'm going to make sure that everyone can hear me. I was told not to join the audio, but with this new setup, I should join the audio, right?
Can everyone remotely hear?
We can hear you. Yeah.
Okay, great. Excellent. So in this case, I leave things as they are. So today I just want to share some of the highlights from my thesis with you. And my thesis is, as you can see on the screen, titled Signatures of Circumbinary Disks that emit a massive black hole binary, massive black hole binaries. And start off, I want to separate this talk into two sections. So first, I want to talk about theory and simulation. The bulk of my thesis work was really theory and simulation, so I'll spend a good amount of time on that. But as I'm also a member of the Nanograph collaboration, I also think a lot about massive black hole binaries and observables from these systems. So I'll tie those the theory and the simulations back to predictions for astronomy. And that will mostly focus on massive black hole binaries and the gravitational wave background. Okay, I was told that there would be a large RU crowd here today, so let's start slow. Okay, I know this is no longer the case, but that's what I was told. So why are binary systems relevant in astronomy? I don't know if I have to convince many of you of this, but there are so many different types of binary systems. There are stars that form mostly in binaries. We have very important historical observations of binary pulsars. Recently, the gravitational wave observations of black hole binaries merging has been revolutionary in the field. X-ray binaries have been a major part of observation in astronomy for a decade now. And of course, there are binary supermassive black holes, which have only indirectly been observed. So we have a very hard time resolving these objects, but we think that many of them are out there. And now we have multi-messenger evidence that these systems might be out there. And then I added some question marks here for all of the systems we might yet encounter, and those I might have forgotten. I also want to say that since we have this unusual setup, please feel free to interrupt me at any time, and we'll try and make this as back and forth as possible. All right, so what is a binary system? A binary system consists of two bodies orbiting a common center of mass. For the lingo, I use M1 as the primary or the heavier object, and M2 as the secondary or the lower mass object in the binary system. And then we can characterize the binary system with three variables. So we can characterize it with the mass ratio, which is the secondary mass over the primary mass, and with this definition always less than 1. We also have the semi-major axis, which for our purposes, we can think of as the separation of the two bodies orbiting the center of mass. And then we have the eccentricity, which sort of measures the flattening of the orbit. And so these three quantities can really define the binary system as a whole. Okay. And then obviously we can take many different permutations of eccentricity and mass ratio and have orbital configurations that are really quite diverse. And so the reason I'm showing this will become clear in the next couple of slides. We essentially have this really large diversity of binary systems that we can characterize with the separation, the semi-major axis, the eccentricity, and the mass ratio of the binary. And this is all assuming that we're thinking of binary systems as a scale-free system, neglecting the physical mass. Okay, having introduced the idea of binary systems, what are circumbinary disks? So we know accretion disks. Accretion disks are flattened disks of gas and dust orbiting a central body, and through dissipated processes, I won't go into much today, the gas in those accretion disks flows towards the central object, and we get accretion, which has many relevant observable properties in astronomy. Now, let's imagine that the central object is no longer a single object, but instead we have a binary system, which orbits the center of mass, and the center of mass is sort of the proxy for the single object that we had in the previous slide. Now, in this case, the disk that forms around the binary system is called a circumbinary disk. And the configuration of the gas around the binary will be very different. The first thing you can note here is that the gas kind of stopped from flowing inwards, and this is due to gravitational torquing from the binary. However, the morphology of the gas as it evolves in tandem with the binary is really quite complex and can't be described analytically. So what we need to do is we need to run numerical simulations that tell us about the gas and how it responds to the binary, and then how the back reaction of that informs us about the binary evolution. Okay, so let's talk about binary evolution in circumbinary disks. In order to model the evolution of binary systems in circumbinary disks, I ran the, as of yet, largest parameter study of binary systems immersed in these gaseous circumbinary disks. And so what you're seeing here is a subset of this simulation suite, where the mass ratio is shown on the vertical axis. Excuse me. And the mass ratio increases going down, and the eccentricity is then shown on the horizontal axis and increases going from left to right. And so a few things to note about these simulations is that, first of all, they're run with the moving mesh code Aracle. They're run in 2D, so we're assuming a sort of coplanar configuration of the disk and the binary. And the reason you're not seeing the binary move is simply because the cadence of these snapshots is taking every 10 binary orbits. So we're just always looking at the binary in the same phase. What you can then discern is the very clear cavity in the center of the circumbinary disk. And this is what I was alluding to earlier when I was talking about the gravitational torques stopping the gas from flowing inwards towards the binary system. But nevertheless, you see streams. I wish I could show you this on the big screen. I apologize, but you can see streams that sort of still manage to go into towards the binary and form these circumsingle disks, or sometimes called mini disks, around the individual components of the binary. And this is due to, still don't really fully understand how this works, but we think that this is due to certain saddle points in the potential of the binary system at which instabilities trigger the inflow of gas at very specific points in the disk. Now, the morphology of the gas around the binary will then tell us how the binary will gravitationally interact with the gas, right? So it'll tell us if the gas sort of slows the binary down or speeds it up, and tells us about the semi-major axis evolution. It'll also tell us about how much the individual components of the binary will accrete. So we can learn about the mass ratio evolution, and through gravitational interaction, we will also learn about the eccentricity evolution. So, so from these simulations, we can extract evolution rates of mass ratio Q, semi-major axis A, and eccentricity E. This is just from running these simulations through to a steady state, and then learning about the gravitational interaction and the accretion over long periods of time after the simulation has reached steady state. Now, having obtained these evolution rates of the binary, we can really summarize the result of my thesis in 3 points. So if you take nothing away from this talk, but this is the one slide you wanna pay attention to. So the first result from these simulations that we published was that the mass ratio of the binary system always increases due to accretion from a circumbinary disk. So what that means is that the secondary will grow in mass faster than the primary, and that therefore the mass ratio will increase. And these binary systems will therefore reach an equal mass ratio within a certain time scale that can be defined and depending on the accretion rate, the total accretion rate from the disk.
That seems counterintuitive. Think that the massive star would attract more.
Yeah, it is really counterintuitive. One of the ways you can think about this is that the secondary orbits closer to the edge of the circumbinary disk. Remember the cavity that I was showing? I don't know if I can draw on here. Can I draw on here? Can people see this online?
Yeah, there's a camera.
So if you remember, there was a, let's see if this is better. Okay. This is the cavity, right, from the circumbinary disk. Now, let's say we have a much more massive primary in the center, and then a secondary orbiting sort of like this. The secondary can just essentially peel off more gas from the disk, whereas the primary sort of loses out. This is just a way to think about it. I'm not convinced that this is the absolute right explanation, but this is what people have been saying since they found these results a couple of decades ago. But we extended this to eccentric binary. So we found that the same happens also for eccentric binary systems. It may be that there are other explanations. I mentioned these saddle points and the binary potential that allow the gas to penetrate into the cavity at really specific points. And those may also play a role, but we really don't have a good analytical explanation for this that might answer your question fully. The second point that is really important in the literature is that the binary separation can either shrink or it can actually grow. And so this is, if you have it all followed the literature on circumbinary disk, it's been a really contentious issue because circumbinary disks have always been invoked as this sort of way to make massive black hole binaries merge, right? But then more recently, simulations have found that the circumbinary disk can actually lead to an out spiral rather than an in spiral into the binary. And so in our simulations, we found that both can happen. So the outcome depends on the eccentricity and the mass ratio of the binary system. So certain binary systems will in spiral, whereas others will out spiral. And then my favorite result is that we actually found that the circumbinary disk guides the binary to a steady state eccentricity. So no matter from what initial configuration you start at, the binary will evolve towards a steady state eccentricity. And this steady state eccentricity actually depends on the mass ratio of the system. Since the mass ratio evolves much, much more slowly than the eccentricity, this can lead to a steady state in the system, reasonably steady state. And so what I'm showing here is simply a binary that was initially on a circular orbit, which is then moving towards a more eccentric orbit. And so this is what the simulations found. And now I kind of want to show you this comprehensive model on a sort of fictional population of binaries. So what I'm showing here are 1,000 binary systems or so, where I've sampled evenly in the mass ratio and eccentricity space. And then in the next few slides, I will show you how each of these binary systems will evolve its semi-major axis, its eccentricity, and its mass ratio. Okay. So this slide here shows the same population, but overplotted with these colors, the semi-major axis rate of change. So you see wherever, again, this would be great up here, wherever there's a blue background, the binary system, the yellow star that you've seen on that part of the parameter space will experience in spiral. So the semi-major axis will decrease. And in the regions of the parameter space where the background is red, you'll see that the binary system outspirals or expands. And then there are these white contours there that really refer to regions where the binary doesn't do much at all, where the semi-major axis almost sort of doesn't evolve very much over time. Now, that's the semi-major axis. Now let's think about the mass ratio and the eccentricity. So you can see that these lines, the stream lines here that I'm showing, they all sort of point to your right? And this is just conveying that the mass ratio of the system grows mildly over time. The gradient is really overwhelmed by the y direction, right? So it's quite steep in the eccentricity direction. And it points towards this kind of steady state in the center of the grid, right? So the more eccentric binaries move down, the less eccentric binaries move up. And so if we then want to get an intuition for how this will work, I'll apply these evolution rates to this population, and we'll see what happens over time. So next, you'll see a video where I've modeled the evolution of the binary systems. You can see each of the binary systems moves along these streamlines towards the center of the plot. So rather than being distributed randomly, after only around, this turned out to be a few mega years, the binary systems move towards this very clear mass ratio versus eccentricity main sequence, I like to call it. And so this is a very powerful result because it tells us that from a two-dimensional parameter space, we can essentially gain a one-dimensional prescription which tells us the eccentricity and the mass ratio of the system that has evolved for a fairly short time in a circumbinary disk setting. Please, yeah.
So you would expect then that over longer periods of time, points will move along the sequence, right?
Yeah.
Will they survive long enough to head to the right stable part of the of this parameter space, or will they inspiral first?
That's a great question. So they would survive for a significant time. We applied this to massive black hole binary populations where we used some reasonable accretion rates. You can see the accretion rate really parameterizes the strength of the semi-major axis evolution. And we found that the mass ratio distribution really shifted towards 1 before the binaries in spiral. But of course, you're right, this is the competing effect. If there are other effects that lead to a faster in spiral, you might in spiral first before everything reaches the mass ratio of 1. Right,
How
so
much do the details of that plot depend on the ratio of the disk mass to the binaries?
Since the binary only needs to really accrete about 10% of its mass, the disk mass sort of sets how far towards the main sequence the binary will travel. But it's only 10% of the binary mass that is required to really reach that steady state. These are scale-free arguments though, so you're right, if the disk mass is very high and fragmentation happens in the disk, and there are other processes that will essentially change the morphology of the gas around the binary, then other things might happen. But in a scale-free setting, you need about 10% of the disk, 10% of the binary mass in the disk accreted in order to reach that steady state. Okay, and so just tying back to the original slide where I introduced these different types of binary systems, this obviously will have implications for binary star formation, right? Where we tend to have a remnant disk as the protostars form. There are other binary systems where we really don't know much about the richness of gas in their surroundings. X-ray binaries may have similar, although slightly different gas configurations. But what I'm most interested in is the example of the binary supermassive black holes, where we do expect that AGN fueling will lead to frequent formation of circumbinary disks. All right. So that already leads me to summary conclusion for the first part, where I've shown you that we've run the largest to date parameter study of binary disk systems, and this led to a comprehensive circumbinary disk binary evolution model and the discovery of this equilibrium distribution of the binaries and circumbinary disks. And again, this is a scale-free model and currently applicable to building any astrophysical binaries. And I've authored and co-authored several papers on this for both massive black hole binaries as well as stellar binaries and stellar mass binaries in a variety of situations. Okay. Now, let's talk about predictions for astronomy. And so when I talk about predictions for astronomy, I'm mostly talking about massive black hole binaries. This is largely the heritage of being part of the nanograph collaboration, but also it's just a really good test case for these models. Okay, so let's talk about massive black hole binary systems. What are they? Where do they come from? Why do we think they're ubiquitous? So we know when we look at the universe, there are galaxies throughout, and we've also learned that many of these galaxies harbor massive black holes, right? Now, we see that galaxies form and evolve through mergers. So if we have two galaxies merging with respectively one black hole at their centers, the remnant galaxy will then contain two massive black holes. Now, one question you may ask, and that has been asked in literature repeatedly, is what happens next? We end up with these two massive black holes likely at kiloparsec scales from one another. And the question is, do they find one another? Do they merge, or do they just float freely in the galaxy? And of course, both can happen, depending on the properties of the remnant galaxy, depending on the dynamical friction background. A lot of outcomes can occur. But a really seminal paper in the 1980s outlines the stages of the evolution of the two black holes in the remnant galaxy, and essentially found that dynamical friction, as well as scattering processes with stars in the bulge, will eventually lead to the two black holes finding one another in the galactic center and forming a binary system. Now, another aspect in a post-merger galaxy that is relevant here is that gas actually is funneled towards the center of the galaxy in a post-merger setting. So you get this binary system forming at the center and gas flowing inwards. And rightly, you might say, this reminds me of something. This reminds me in the circumbinary disk introduction I gave earlier. So we have gas flowing towards a binary system, and therefore you should form a circumbinary disk. Okay. So what that implies is that circumbinary disks actually do govern massive black hole binary evolution in the final stages of the system evolution. And that means that we can use these circumbinary disk-driven binary evolution models that we obtained from our simulations, and we can look for signatures of these evolution models in the massive black hole binary population. By signatures, I mean things like what I've shown you earlier, where the binary eccentricity and mass ratio are correlated due to dynamics occurring in the circumbinary disk. Okay. The reason this is really relevant right now, and the reason we want to do this right now, is because the Vera Rubin Observatory will likely start taking data next year, and there have been suggestions that this telescope may detect up to 100 million massive black hole binaries. This is a citation to a paper here that claims this. I think there are many variables at play, but the expectation is that this is one of the first observatories that will really detect many of these sources. And the question we want to ask is, in this large population study that will likely be possible with upcoming telescopes, is can we detect signatures of circumbinary disk dynamics in that population? And can we say something about the past evolution of these binary systems by observing the properties? So the way we want to do this theoretically first, because we don't have the data yet, is by obtaining a sample of massive black hole binaries from cosmological simulation. So I told you earlier about the galaxy mergers leading to the formation of massive black hole binaries, and that we can then model that post-galaxy merger evolution of the massive black holes using the models such as dynamical friction, the scattering, and circumbinary disk. Now, large cosmological simulations, such as the illustrious simulation, contain information about galaxy mergers. So we get this large cosmic web where repeatedly galaxies merge with one another. And what that means is, from these simulations, although their resolution is not good enough to really model the small scale evolution of the massive black hole binary, we can get sort of initial conditions and sort of a population sample of massive black hole binaries that we can then evolve semi-analytically. So we get these galaxy mergers, and from those galaxy mergers, we get information about massive black hole binaries in the universe. So we get the individual masses of the black holes, we know their separation, their distance to us, so their redshift, and we know something about the host galaxy properties. And so by obtaining that information from cosmological simulations, we end up with a sample of just under 3,000 massive black hole binaries with the initial conditions such as mass ratio, binary mass, again, separation, and redshift to it. And this is all from a project within the nanograph collaboration that I'm part of. It's called Holodeck, and we're essentially evolving these massive black hole binaries obtained by cosmological simulations to learn about their properties close to merger, as well as the gravitational wave background data like we'll see. Okay, so I told you that we modeled the formation of the massive black hole binary in a post-merger galaxy using dynamical friction and other models. And so applying that to the massive black hole binary systems found in cosmological simulations, we eventually lead to this population of just under 2,000 massive black hole binaries that can then be evolved with our circumbinary disk model. Okay. And so here I want to show you an example of how the circumbinary disk driven evolution will affect the properties of massive black hole binaries that will be observable by the Vera Rubin observatory. So here I'm plotting the mass ratio on the horizontal axis and the eccentricity again on the vertical axis. So this familiar parameter space I introduced to you earlier. And on the left-hand side, the left panel, we're going to look at the evolution of the eccentricity and mass ratio of the binary when all sorts of galactic processes occur, but we don't include a circumbinary disk. So the binary may interact with the stellar background with through dynamical friction with dark matter and gas, but it's not going to form a circumbinary disk. It will, however, also emit gravitational waves and evolve its parameters as a result. On the right-hand side, we're going to see the evolution of the same population, but including a circumbinary disk. So as I let this video run, you can see that the left-hand side shows hardly any movement. But on the right-hand side, even though the circumbinary disk is competing with all sorts of other processes, the binary finds its circumbinary disk prescribed equilibrium state really fairly quickly. And this signature, which relates mass ratio and eccentricity to one another, really helps us discern a structure in the parameter space of massive black hole binaries. So if we exclude circumbinary disks from the equation and we want to interpret the massive black hole binary population that we will probe in the future, all of the parameters will be randomly distributed. It'll all just depend on hierarchical structure formation, what black holes find one another. There'll be pretty much a random structure to that. If we include circumbinary disk dynamics, the structure that emerges directly links the mass ratio and the eccentricity to one another. And so it kind of finds a structure in the chaos of it all. So that's really, oh yeah.
So what exactly is the observational signature that Rubin was seeing? I mean, there are existing surveys that are anywhere from 4 magnitudes to 1 magnitude less sensitive. And at 3.5 magnitudes or something like that, it's a factor of 100 down in volume, but that means there ought to be a million objects if there's going to be 100 million in Rubin. So I'd like to know, what is the signature, and why hasn't it been seen? And so what's the...
Yeah, so you're asking how we detect these things. Yeah, so it's really a variation in the luminosity that should tell us if a particular AGN is a binary or not. But as you can imagine, this is really hard to do because AGN are naturally variable. So the Vera Rubin Observatory I believe probes are larger volume, so it doesn't.
So going to look at somewhere between a quarter and a third of the sky, whereas other surveys are full sky. And
So which surveys,
well, so for example, Atlas has been collecting the sky for 8 years now. And it's about, I don't know, 3.5 to 4 magnitudes less sensitive than Rubin. And if you take 10 to the 0.6 m, that's, a factor of 100 down. Pan-STARRS has observed 3/4 of the sky with a sensitivity of maybe down by magnitude and a half. So 10 to the 0.6 m is 10%. So all of these surveys have massive numbers of these putative things if Rubin can detect 100 million. And so the question is, why hasn't anybody seen them? Why hasn't anybody looked for them? Is there,
Or what should we
yeah,
do?
is it periodic periodicity? People have certainly looked for periodic AGN, but we've not seen them very much.
so that there are, I see papers on the archive claiming to find these kind of periodically variable AGN, and then fairly often, as you say, they're kind of debunked, and we don't really have any certainty about binaries in there. Another issue that might clear this up is that you don't only want to observe the AGN over a long period, you also need a good cadence so that you can.
These surveys have better cadence than Rubin. These are 4 times nightly in the case of Atlas, for example, as compared with Rubin that will be once every couple days.
Okay, maybe we should talk about this because I'm not an observer, so it's great to be here.
So I have to run right now. Where are we?
I'll be here for a couple more hours after this. Why don't I email you? I'll get your email from someone here. Yeah.
Thanks.
Yeah, thank you. It should be interesting. Okay. Yeah, I'm curious why people are excited. There's a sort of bimodal distribution of astronomers who are really excited about finding binary AGN with LCC or Vera Rubin, and then others who are less excited. Okay.
Well, I think we're seeing the trade-off between skepticism of Rubin's claims versus experience and maybe lack of experience with searches in existing materials.
Yeah. And this is one of the issues, right, with theorists and observers. I think theorists like myself are really excited, but then we kind of come up against the realism of people who have actually done this. But yeah, great. So I do think, however, that the pretty certain detection of the gravitational wave background this year gives us some very good reason to believe that massive black hole binaries do exist and do form frequently in the universe. And so if you still have time, I believe I'm maybe a bit over time. Yes, apologies. I'll talk very briefly about the gravitational wave background, and we can talk later about the detection from the nanograph collaboration. All right. So let's say we have massive black hole binaries forming in post-merger galaxies, and those binaries find each other and emit gravitational waves as they inspiral. Then we may get a couple of sources here and there. The black holes will grow as they merge. All is good. Okay. So let's imagine we're on Earth here. I don't know how many of you can see this. And we have a source going off nearby. We would expect that if we have a detector that can detect these gravitational waves, we would see a single source. We may also get 4 sources that are going off around the same time or continuously emit gravitational waves, and we may also be able to distinguish those. However, what the gravitational wave background really means is that we have this background of sources that are all continuously emitting gravitational waves at the same time at a variety of frequencies. And at that point, you really can't distinguish individual sources. So what we're seeing then is a sort of background echo of gravitational waves being emitted by massive black hole binaries throughout the universe, everywhere, all at once. And we see this spectrum that is not attributed to any single source, but to the cumulative emission of gravitational waves throughout the universe. We can relate this signal to a very simple equation that I've shown here on the slide. So pretty much the only equation I've shown you. And there's a good reason I'm showing this. And this strain H relates to the frequency in a particular power law way. It also relates to properties of the massive black hole binaries, in particular, the chirp mass. So let's say we've taken our massive black hole binaries from cosmological simulations, and we plot the gravitational wave background spectrum from these sources. This is what it looks like. It's just a power law relationship. Okay. Now, I've highlighted here the the chirp mass of the binary system, and you can see that it relates to the mass ratio of the binary, right? But we've just learned that the mass ratio of the binary is affected by accretion from a circumbinary disk. So therefore, the loudness or the strain of the background depends on the mass ratio, which depends on the prior evolution through a circumbinary disk-driven accretion flow. Okay. So if the circumbinary disk increases the mass ratio, increases the chirp mass, it will increase the strain in the gravitational wave background spectrum. And we can apply this here to our sample of massive black hole binaries from cosmological simulations. You can see a mild increase in the mass ratio leads to a mild increase in the gravitational wave background spectrum. Now, the light green line here is just assuming a very conservative accretion rate overall. If we apply larger accretion rates up to Eddington accretion rates, we see that there's up to an order of magnitude increase in the gravitational wave background strain. The reason this is not reaching the nanograph detection strain that I've plotted here, and we can talk about that later. This is really to do with the volume sampled by the cosmological simulation that I used for this. Okay, I'll end here. This is part 2. Basically, this part is really showcase the application of circumbinary disk-driven evolution models in massive black hole binary systems. Showcase that this equilibrium eccentricity should be clearly visible in binary populations evolving through this channel, and also boost the gravitational wave background amplitude to some degree. And thank you for your attention, and apologies for going over time.
I think since we're over time, we can officially end it there, but I'm sure Magda would be happy to stick around if any folks have questions. So.
Yeah. Thanks.
Great. Thank you again.
Yeah, thank you.